Hi everyone, Mr. Lee here. In this video, we're going to go over the idea of center of mass and the momentum of a system. Okay, so let's start off with the definition. What is the center of mass? So, simply put, for any object, you can find the center of mass by just taking their entire being and just like crunch it down to like the average location of all the pieces and the parts. This is what I mean. So if we have, let's say we have a ball, right? And this ball has equal mass distribution throughout the entire ball. If we were to get that ball and we were to crunch it down, we would get a mass right there, right in the middle, right? And that's why we call it the center of mass. And this idea applies to other objects such as, let's do a donut, yeah. So if we have a donut, right, which is just a circle within a circle, right, and on the outside, let's make this a, I don't know, one with red frosting. All right, so we have a red frosting donut, okay? And if we were to get that donut, right, you were to get that physical donut and you were to smush it down, the location, the average location of all of the parts of the donut would be right in the middle. Even if there's nothing there, right, because it's a donut hole, it's like empty space, the center of mass can be said to be right in the middle. Something cool for us as human beings, we too have a center of mass. I'm going to draw a quick stick figure, right? Hello. Okay, so that's my stick figure. For males, you can find your center of mass. So if you touch the middle part of your chest, you can feel your sternum, right? That hard bony part. And then if you go down, 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 right where your sternum ends, that's like where your diaphragm is. Right, like around the solar plexus area, okay, right where it becomes soft, that's where your center of mass is, usually for males. And for females, it's slightly lower, right around the belly button location. So human beings have center of masses, donuts have center of masses, all objects have center of masses. Now, with this idea of center of mass, we can apply this to systems. Oh, speaking of center of masses for objects, one cool little trick that you can do for any object to find the object's center of mass. So let's say this pen, right? So visually, if I take a look at it, I can be like, all right, the center of mass for this pen is like right, it should be right around the middle. But the best way to figure this out is what you can do is if you get your two fingers and you bring your two fingers close together, okay? Now do this slowly. Right where the location of your two fingers meet, that's where the center of mass is. And we know that's the center of mass because you can balance at that location. So whenever you have a support underneath the center of mass, we call that a balance. All right, and you can do this with all kinds of objects. So if we were to take this idea and we were to apply it to objects that are not like equally distributed, like a human being, we can like use this idea for the system as well. For example, let's say we have a baseball bat, right? So we have a baseball bat. So if I take a look at the baseball bat, I can tell that the right-hand side of the bat, this part, okay, there's a lot more there compared to the left side of the bat. So because the masses are not evenly distributed, I can make the claim that the center of mass won't be right in the middle of the bat, but a little bit higher towards the right side, and that's because there's more mass located there, right? Because center of mass tells you the average location of all the masses. So that's something that is important to know. If we were to take a look at a system, so for example, if this is my viewpoint, right, and I say there is a object here and there's a object here, and this box represents my system, I can say that the average distance between these two objects and the average mass between these two objects is my center of mass. So if I were to say that, let's say this is object 1 and this is object 2, if both objects 1 and object 2, if they have equal mass, the center of mass will be right in the middle. Okay, because they have equal mass. But if I were to say that object 1 has a greater mass than object 2, then the center of mass would be closer to object 1 because it's talking about the average location of the mass for a system. Okay, so right now we just discussed what the idea is behind center of mass, and this will actually pop up again later on in the physics course. But how can we apply this to momentum, the center of mass for a system, the momentum of a system? Okay, so let's do a quick recap. So we know that momentum for a system, it cannot change, can't change unless there is a outside force. There is a outside force, and we call that impulse, right? If there's an outside force acting on a system, the momentum can change, and we call that change in momentum impulse. In terms of energy, we call that work. When work is done to a system, the energy changes. But for momentum, we call that a impulse. Okay, so knowing this, we can say that the center or the momentum for a system, it'll never change. So this is what that means for us. So I figured the best way to show you the how we can look at center of mass and momentum is through the use of simulations. So I'm gonna be talking here, and whenever I say something relevant, you should definitely write it down. So here we have two different objects. We have object 1 and object 2, and we can see that object 1 has less mass than object 2. In fact, we can see down here that object 1 has a mass of 0.5 kilograms and object 2 has a mass of 1.5 kilograms. And the simulation is going to give it a velocity. Object 1 will have a velocity of 1, and object 2 will have a velocity of negative 0.5. And it's negative because it's going to be headed towards the left. So what I want you to take a look at is right there. This X marks the center of mass. And it's closer to object 2 because object 2 is more massive. Now, what I want you to focus on here is the motion of the center of mass. Okay, so this is what we know. The system consists of two objects, objects 1 and object 2, and both of those objects, they have momentum. And if I take a look down here in this diagram, I can see that object 1 has a momentum going to the right, and object 2 has momentum going to the left. So if we were to add these two together, I'm going to zoom in a little bit, we have this total momentum that's like going to the left. It's not big, but it's there. And in fact, we can see this if I were to click the momentum arrows. Okay, so once again, this momentum is going to the right, this momentum is going to the left, and the center of mass has its own momentum. Now, what I want you to do is I want you to take a look at the X there as the two objects are coming closer together and as the objects interact and bounce apart. Ready? Let's do it. Okay. Did you see that? I'll play that one more time. Wonderful. I'll play this in slow motion and I'll talk this through. So these are the things that you should be taking note of. One, we can see that the center of mass has its own momentum. It has its own velocity. Because there are no outside forces, that momentum does not change. And it's because there are no outside forces. The momentum stays constant. And we can see this especially if we make the two momentum equal to each other. So let's make it 0.5, like so. Alright, so we can see here, and we'll make this velocity -1. Okay, so according to this diagram, the object 1 has a momentum of 0.5, and object 2 has a momentum of -0.5. And if we take a look at the diagram here, when we add the two momentum together, our final momentum is 0. And what that means is that this center of mass will have a momentum of 0. And that's because the total momentum of the system adds up to 0. So if that's the case, this center of mass, it should not move, even after they collide. Let's take a look. See right there? The momentum does not it doesn't change, right, even after the collision. So we can say that the center of mass throughout this entire process, the average location of the masses will always be right there. So the further apart the two objects get, it doesn't matter because the average location will still be right there and it doesn't move. And this is extremely useful when we're approaching ideas such as 2D motion. And this, we'll come across this, but I want you to see here how the center of mass is changing as the two objects are moving. So if I were to click the velocity vectors, we can see that object 2 is moving down and to the left, and object 1 is moving up and to the right. And when the two objects collide with each other, because there are no outside forces, the center of mass, well, with its own momentum, the system's momentum, that will not change. The center of mass will have a constant motion. So let's take a look. I'll do this in slow motion so we can see. Okay, so even after they collide, the center of mass, it keeps on moving normally, right? It doesn't change. The momentum does not change. The momentum for the system does not change. However, we can make the center of mass, the momentum of the center of mass change if we add a reflective border. So what this means is that these two objects, once they hit the outside edge, it can bounce off of it. And when that happens, that's considered to be an outside force. And because there's an outside force, the momentum of the center of mass will change. Let's take a look. So far, so good. The center of mass doesn't change. Boom. But as soon as it touches the outside edge, see how the momentum of the center of mass changes. And that's because the momentum for the system has changed upon hitting the border, because the border is considered to be an outside system. Okay? All right. So how does this apply to us with our class, and how can we use this knowledge to explain things? Okay, so the idea is that the system center of mass, the momentum, it does not change. Okay, and so the types of problems that you might get deal with this very core idea. So for example, if we have, let's say, a rocket, right? That's my rocket, and this rocket goes up, pew, and upon the maximum height, right, where the velocity, the y velocity is 0, the rocket explodes, and we have pieces that fly off. We have one piece that lands out here, and we'll call this position negative x, and the question can be, where will the other piece land? Right? So if it splits off into two pieces, one piece lands at negative x, where will the other one land? Now, the way that we can approach this problem now is through the use of center of mass and momentum. At the maximum height, we learned that the velocity is 0. The y velocity is 0. It's like kind of frozen up there. So if the maximum y velocity up there is 0, that means the momentum of the system is 0 at the maximum height. So if that's the case, that means that the center of mass will have a momentum of 0 as well. Okay, so this is a big idea. We learned that one piece landed at negative x. So that means that this one piece had, I'm going to call this mass 1, right? Mass 1 had a piece that had a negative momentum. Therefore, object 2, mass 2, or excuse me, object 2 that flies off in this direction, it needs to have a equivalent momentum. We can say that it is momentum 2, right, and it's positive. And what we can say here is that momentum 1 is equal to momentum 2, except momentum 1 is negative. And so if object 1 landed at a position negative x away, we can say that object 2 landed at a position x away. And the positions will be the same. And that's because the center of mass, if you take a look at the average location between these two, it'll just be right there, right where it started. And we know this to be true because if the rocket just shot up and it doesn't explode, it'll just come right back down to its original location. And so the center of mass does not move. And if we were to give this like numbers, we can say if negative x is, I don't know, negative 10 meters away, we can say x is just 10 meters away. So they landed at equal positions. Okay? So that is one way to approach it. Another way that we can approach it is through the use of projectile motion. So instead of having an object just being shot straight up, if we have an object and it is shot at an angle, pew! Okay, and let's say up here at its maximum height, right there where it's still moving forward, so there is a velocity, okay,
we'll call it Vx, right? It's still moving forward. At that moment, the pieces explode. Okay, so when the pieces explode, we learn that I don't know, one of the pieces it shoots further out. Okay, and the question might ask, so it shoots further out. Where will the second piece land? So the best way to approach this one is, if we know that one piece shoots further out, we gotta think. We gotta think here. This object, it had a momentum, and this momentum was a forward momentum. Okay, so we had this positive momentum before the explosion. Because there were no outside forces, this object will still have its forward momentum if we were to look at the center of mass. So the best way to approach this is to think about, where will this object have landed if it never exploded? So I'm going to do this in red. It's going to outline, so it goes up, right, and then it would have landed right here. So if the object, if it never would have exploded, would have landed right there, that means that the second piece that flew off, okay, so this is the whole piece, and this is piece one. So the second piece that exploded, it would land in a location so that the average center of mass would be right here. So between position 1, this is where it would have landed if it didn't explode, and let's say somewhere around here, this can be position 2. And we can say that the second piece would have, like, once it exploded, kind of like falls like there. We can say that this object would have landed behind the original location, because the average location between these two objects would be right here, and that's where the center of mass is located, right there. Okay, and so whereas one object flew further out, the second piece would have still gone out forward a little bit, but not as far. Okay, yeah. So those are the types of explosion type of problems. Now, another way that we can think about this is through the lens of a raft. So this was a little bit tricky because there's no explosions here. There's like the multiple pieces are like all within each other, and so the question is, if you have a raft, right, and this raft, it has, I don't know, the center of mass is right there for the raft, and if you were to stand right there on the raft, okay, and let's say for the sake of our problem that the mass of the person, I don't know, it's like 100 kilograms, and the mass of the raft is also 100 kilograms. Okay, so I'm saying here that the person and the raft, they both have the same mass. So because they have the same mass, the center of mass would be right between these two objects. So like right around here. Right around here is the center of mass for the system. Okay, so the question now becomes, if this person were to walk forward, what would happen to the raft itself, and how will it move? All right, so if that is the question, once again, the best way to approach this question is to take a look at it through the lens of center of mass. There are no outside forces, so no matter where the location is, the center of mass must remain along this dotted line. So this is what it means. Let's say if the person originally started here, let's say the person ended up somewhere here. Okay, so the person is all the way out here because they were walking along the raft. So if this were the case, we need the average location. I think I drew that a little too far. I'm going to draw this a little closer. All right, so we'll put that like here-ish. There we go. All right, so the person walked forward on the raft, and the person has a new location that is to the right. Where would the raft be? So we know that the average location of the masses has to be right here along this dotted line, because that's the center of mass, and there are no outside forces, and so there was no momentum change, and so the center of mass will remain there. That means the center of mass of the raft has to be somewhere out here-ish. I'm trying not to make it exactly the same, right? So it has to be somewhere out here. That's because the average location between the raft, let me draw this out, there we go. Okay, the average location between the raft and the person will be represented as the center of mass for the system, which is like right around there. Okay, so as the person walks forward, the raft itself will move backwards. And so how can we approach this through the lens of momentum? So we can say that the initial momentum for the entire system was 0, right? They were just standing there. And so if the person gains a forward momentum or a positive momentum, that means the raft will have to have a backwards momentum, aka a negative momentum. And that's because if we add the two together, it will go back to the momentum being 0. And so that is why, like, you can try this yourself. Like, if you have a raft and like a lake or a pool, if you're to walk forward on like the boat or the kayak will move backwards. But in real life, the person and the raft, usually they don't have the same mass. So how can we approach this through like a more realistic lens, a realistic point of view? So let's say the mass of the person is, let's say 100 kilograms. And we say the raft is, I don't know, let's say 200 kilograms, right? It's double the amount. Okay, so in that situation, okay, as the person is walking forward, the raft will also move backwards. Well, actually, let's do the center of mass problem again. So we have the center of mass for the raft right there. The person has a center of mass right there. And because the raft is more massive, I'm going to draw the center of mass line closer to the center of the raft. So this is where the center of mass is for the system, right there. All right. So when the person walks forward, the raft will also gain a momentum backwards. So the idea is the same. The momentum of the system is still going to be 0. The person will gain a positive forward momentum, and therefore the momentum of the raft will be a negative momentum. But because the masses are different, how much the raft moves will change. So we can say that if the person, well, momentum is mass times velocity, right? So if the person has a smaller mass, that means with respect to the raft, the person will look like they are moving faster compared to the raft, which has a bigger mass. Therefore, the person or the raft will look as if it's not moving as much. And so that's why in like a real life scenario, if you have a raft or like a kayak or like a board that you can stand on, when you walk forward on the board, it feels as if the boat or the raft underneath of you doesn't move as much or barely at all. And that's because the boat or whatever thing you're standing on just has more mass. It's moving, the velocity is just pretty much smaller. Okay. And a couple of questions that we came across in terms of multiple choice, it had the same idea. And you could try this if you have one of those rolly chairs, right? So one of those rolly desk chairs. I'm going to do my best to draw one of those. Okay, so there we go. Okay, so if you have one of the rolly desk chairs, right, and you're sitting on top of it, let's see, this is a horrible sketch. I don't know why. But right, now it kind of looks like you're just like a 5-year-old. Okay, so if you're sitting on this rolly desk chair, and let's say you have something heavy, right? You have like your book bag, and your book bag filled with, this is my book bag, filled with your old textbooks, right? Let me draw the textbooks inside. So there we go. All right, filled with all of your old textbooks. Okay, so the book bag is pretty heavy because you're just sitting there. And by the way, if you do this, well, you should be careful so that you don't hurt anyone, but make sure you're doing it on like a hardwood floor to reduce the friction, because if you do this on carpet, you're not going to get the same effect. So initially, if this is a system, the system's initial momentum would be 0. Okay, and so if you throw the book bag full of books forward, you and the chair, you will move backwards. Yeah, it's cool. And yeah, so that's it. That's center of mass. That is how we can use momentum and center of mass together. A lot of different scenarios. These scenarios that I came up with, they popped up when I was looking through old AP exams, and these are the type of questions that you'll be asked. So my suggestion to you, strategy-wise, is to 1, okay, locate the center of mass. Okay, 2, okay, identify outside forces. So usually when we're talking about outside forces, they will call it a open or a closed system. So if it's open, then there are outside forces. Yes to outside force. If it's closed, there are no outside forces. All right, and your job becomes, or your life becomes a lot easier if it's a closed system. Identify what is the system's momentum, because if there's no outside forces, that means the momentum will stay the same. Okay, and usually the type of problems we'll talk about the location of different objects, much like the rocket problem, or like the raft. Okay, and just think about it that way. Right? Think as if the objects never broke apart, or if we're just looking at the object as a whole. All right. So this was a little bit of a longer video, but this is the culmination of this entire unit. The idea of center of mass and momentum. Until next time, I'll see you later. Bye-bye.